Today we'll talk about magnetic force on current-carrying wires, and this extends the work that we did last time where we talked about the magnetic force on a moving charge and the magnetic force on a straight wire, both of which in a uniform magnetic field. Now we'll consider wires that might not be straight, that could be curved in any way, and in fact you could apply the same technique that we'll use to consider curved wires in non-uniform magnetic fields as well, although we won't do that today. And then we'll consider closed loops of current-carrying wires to look at the forces and the torques on them. So we start with just a quick review of the things that we talked about last time. I just want to remind you that there's something called the Lorentz force. So electricity and magnetism is governed by Maxwell's equations, which tell you how the electric and magnetic fields interact. We've talked about that a little bit in this course, and eventually once we write down all of the different effects of electric and magnetic fields, we'll join them together in Maxwell's equations. But the connection between electromagnetism and Newton's laws, mechanics, comes from a force, and that is the force that electric fields exert on charged particles and the force that magnetic fields exert on charged particles. So together with mechanics and the Lorentz force, Maxwell's equations will give us this complete theory of electromagnetism. So what is the Lorentz force? It's just the sum of the two forces that we've seen already. So the electric force is on a charge, Q, and it's just given by Q times the electric field. And the magnetic force is also on a charge, but you only get a force if the charge is moving. So it's QV crossed together with the magnetic field vector. So this is the electric force, and this is the magnetic force. So we say that the sources of electric fields are charge, and charge are also forced by electric fields. And then the sources of magnetic fields, it turns out, are currents, moving charge, and it turns out that moving current, moving charge, also feels a magnetic force. I just want to remind you how we calculate that thing. The vector product, this thing right here, V cross B, is a mathematical thing. It's a different kind of product than the scalar product or the dot product. So the vector product is also sometimes called the cross product. And if you have two vectors, let's just use V cross B, V cross B, then their result is going to be another vector which has magnitude V, magnitude B, sine of the angle between V and B vectors. And that looks a lot like the scalar product, like the dot product that we've seen. But that's just the magnitude of the resulting vector that you get when you multiply these two things together. We also need to specify the direction. And the direction is, we say, perpendicular to both and given by the right-hand rule. So if we have a magnetic field, let's say that it's out of the page. So remember, we represent an out-of-the-page vector field with little rocket heads pointing towards us. And then we have a charge which is moving with some velocity to the right, maybe. So the velocity vector points like this. So we have a magnetic field out of the page and a velocity vector to the right. Well, you tell me the direction. It's going to be perpendicular to both, so that means that we form a plane by the vector that's coming out of the page and the vector that's going across the page. So that would be a perpendicular plane to the screen that you're looking at right now, basically a horizontal plane. That means that the direction of V cross B must be perpendicular to that. That's what we say here. It's perpendicular to both, so it's perpendicular to the plane formed by V and B together. And therefore the I keep wanting to say force, but unless you multiply it by q, it's not a force. The direction of v cross b has to be either up or down. So just by that statement that the direction of the cross product is perpendicular to both, you know the line along which the vector must point, and in this case it must be up or down the page. Now we choose which one it is by using the right hand rule. And we do that by taking the fingers of our right hand and holding them up to the right along with the first vector. So you point your fingers along the first vector, v. So now my fingers are pointing to the right across the screen. And then I want to close my fingers in the direction of b. So I see that b points out of the screen. So that means I want to twist the wrist of my right hand so that my palm is facing me, and then close my fingers towards me, and I see that my thumb points down. So it chooses the direction down. So v cross b is down. And it could only have been along this direction, either up or down, because it has to be perpendicular to both of those v and b vectors. So we'll use that today, of course, and in fact for the rest of the semester when we talk about magnetic fields, we'll have to use this cross product. We have this equation for the force of the magnetic field on a moving charge, but we could also use that for the force of a magnetic field on a current-carrying wire, because of course a current-carrying wire is nothing more than a bunch of charges moving. So let's consider a straight wire. We already wrote down the equation, but let's just remind ourselves where that comes from. So let's say that it's this straight wire, and it turns out that it has a current that's moving in this direction. And then let's assume that there's a magnetic field maybe in this direction here. And we'll just make it uniform. So there's some magnetic field pointing like this. So what we can do is we can break this up into a bunch of little chunks of charge, and then the total force on the wire will be equal to the sum of the forces on the chunks. So we could call that FBN, where n goes from 1 to capital N, as we're used to doing. So then we consider one chunk, and let's just place it along an axis. Doesn't really matter where that axis is, so let's say that it has a width of delta x, and there's a charge in that little chunk, which we could call Qn, and that chunk is moving with some velocity Vn because of the current. So it's moving along the wire. So let's see what that means. So the force on that little chunk is going to be, based on our first equation, it's going to be Qn times Vn vector crossed together with the magnetic field at that position. So I guess we could say the magnetic field at position xn there. Now what can we do with that? Well, the cross product is going to give us a magnitude, if we were to look for the magnitude of it, and that would be VB sine theta. But we don't need to do that right now. So let's just look at what we mean by Q times V. Well, Q times V, if we look at this thing, the current is the amount of charge that goes past a given plane, which we could call delta Q, divided by the amount of time that it takes for that delta Q to go past. So if we take the delta Q to be our little Qn, and just imagine it to go past this plane, how long does it take for it to go past the plane? Well, it's going to be exactly given by the velocity there. And so the velocity you can think is like delta x over delta t. So that tells us that the amount of time that it takes to go past is equal to delta x over v. So then we can say that if we take the amount of charge to go past some plane to be Qn, and we take the time to be delta x over Vn, then we could write Qn as I delta x over Vn. So I've just rewritten the moving charge in terms of the current that we have. So I can write then this as I delta x over Vn. And then I still have the Vn cross B. The B is, as we've defined it here, uniform, so it doesn't matter where it is, so it doesn't really depend on xn. And the V is really just the drift velocity. So that's the velocity at which electrons are moving through this wire. So it doesn't matter what that is, but that's what we're going to have in the Vn here. That will cancel out, and we'll just get a vector in the direction of the Vn, which is in the direction of the current. So what do we get? Well, all of those things can be pulled out except for the delta x. So we get I hat cross B times the sum of the delta x. And we find that the sum of the delta x is just the length of the thing, the length of the wire. And so we could write that as I L I hat cross B. So I've just put together the total length, which we got from adding up the total chunk lengths, and it's crossed together with B. Now what we usually do is we say, well, I'm just going to call this a vector, the L vector. So it's a vector of length L, the length of the wire, and it points in the direction of the current, which is the direction that I've chosen that x-axis to point. So we get a new equation, the one that we introduced last time, which is the force on a current-carrying wire is IL cross B, where L is a vector that points in the direction of the current, and B, of course, is the magnetic field vector. That's what we're going to use today, although we're not going to apply it to a long straight wire. We're going to apply it to little chunks of wire, just like we did just now. So let's look at how this is going to work. So we have this equation, IL cross B, for the force of a magnetic field on a long straight wire. But we could use this for a non-straight wire. And in fact, we could use it for a non-straight wire in a non-uniform field. So here's a wire, and let's say that there's some current moving in that wire. And then we have a field which could really be anything. So it could be, we could just draw it however we like. Some magnetic field that's sort of going everywhere in space. Oops. So maybe it looks like this. And it might have a different magnitude at different places. Something like that. So what is the net force on that wire due to this non-uniform field? Well, the net force is just like we said last time. It's going to be equal to the sum of the forces on every little chunk. So we want to chop up the wire into chunks. Chop, chop, chop. And then we consider the force on every chunk. And what will that force be? Well, it will depend on the particular length vector for that chunk, which we could call Ln, like this. And it will depend on the magnetic field vector at that position, which we could call B at whatever that position in space is, R. So it's going to be the sum of current, that's the same everywhere in the wire, times the particular chunk Ln crossed together with the magnetic field at the position of Ln, which we could say position Rn. I guess there should be an N on this little R here. Now that's completely general. We're gonna probably just use uniform fields, but you can see that you could apply this equation for a straight wire just for a small chunk, which is approximately straight, in a region where the magnetic field is approximately uniform. So we just use our basic equation for straight and uniform field, and we can apply it to every little chunk, which we make small enough such that that's approximately true. And of course, this equation is really just an approximation, and so eventually we'll want to make an integral, which will then lead us to the exact result. Doing that in general for a curvy wire like this and a weird field like this might be hard, but it's possible. But doing it for an example, but we can come up with some examples that are much easier but still use the basic principle. So let's try and do that. So we'll consider this example. We have a wire that's bent around the edge of a table, and half a meter of that wire lies flat on the table, and then it bends through a quarter circle with a radius of 10 centimeters, continues 1 meter vertically to the floor, and then there's a uniform magnetic field pointing perpendicular to the plane of the wire. So let's draw it. So let's say we have a table. And the wire has half a meter along here, and then it makes a quarter circle, and then it goes a meter down to the floor. And it's a current carrying wire, so we'll just assume that there's a current that goes like this. So somehow those two ends are connected. And then the magnetic field is perpendicular to that whole thing. So maybe let's just assume that the magnetic field points into the page and that it's uniform. So the magnetic field is everywhere uniform, like this. And the question is, what is the force on that wire, meaning what is the net force on that wire? So let's just draw a couple extra little things on here. Let's give it a length. So L1 is equal to 0.5 meters, and then the other straight part is L2, and that's 1 meter. And then we could draw a little circle here. So that circle has a radius of 10 centimeters, so 0.1. So we have straight connected to circular, connected to straight. And the question is, what is the net force on that thing when you have a current I and a magnetic field of magnitude B? Well, we should do some qualitative analysis first, and that's just to say that the net force can be thought of as three pieces. So it's the force, it's the force of the magnetic field on L1 plus the force of the magnetic field on the little circular loop, we could call that circ, plus the force of the magnetic field on L2. So what are those things? Let's give ourselves a coordinate system. So let's say that we have x, y in the plane of the page. Then the force B on L1 is going to be I, L1 vector. So what do I mean by that? I mean a vector of length L1 that points in the direction of the current, so it looks like that, crossed together with the magnetic field vector. The circular part, we don't actually know yet. That's going to be the main part of this problem, so I'm just going to leave it as that. And then the last part, the force on L2, well, we have an L2 vector that points like this, and the force is just going to be I, L2 vector, crossed with B. So let's do those first and third quickly. So what is the direction of L1 cross B? Well, do it with your right hand. Put your fingers along the direction of the L1 vector. So extend the fingers of your right hand along the L1 vector. That's to the right across the page, across the screen. And then you want to close your fingers in the direction of B. B goes into the page. So that means that you're closing your fingers into the page and your thumb points up the page. So it had to be either up or down the page. In this case, it's going to be up the page. So this is FBL1 vector. Now the one that goes down, put your fingers down the page, your right hand down the page along with L2, close your fingers into the page, and then you'll get your thumb pointing to the right, FBL2. Better just check that. Fingers down the page, close into the page, and your thumb points to the right. So we can write this as the magnitude of that force, each of those forces, so it's going to be I, L1, B, sine of the angle between L1 and the B vectors, times the direction that I've found, which is, I guess, the positive j hat direction. Now, what is sine of that angle? Well, you can see that L1 points along the page and B points into the page. So if you make a finger pointing into the page and a finger pointing across the page, you can see that that's a 90-degree angle. So this is going to be 90 degrees. And then this whole thing will be sine of 90 is 1. So that's just going to be IL1B. Then we still have whatever that force is due to the circular part. And then finally we have the magnitude of the third one, which is IL2B, sine of 90, times the direction, which is going to be in the positive x direction, so that's the I direction, I hat direction. So we're almost done. We're almost done finding the net force. It's the sum of these two so far, but now we need to figure out what this FB circ is. And we should do a little bit more qualitative analysis to try and figure out what that should look like. So if we consider only that circular part, so it's a quarter circle, looks something like this. It's going to have an eye that points along the curve there. And maybe I should place it on a coordinate system. That might be useful. So I'm going to do that for now. Now, what is the direction of the force on this thing? Well, let's just consider an arbitrary chunk. So we're going to chunk it up. So let's consider this chunk here. So that's going to have a little delta L vector. And we'll call it the delta LN vector. The B at that location, of course, is still into the page. So this is the B at that vector, at that little chunk's location. And what will be the direction of the force then? So we point our fingers along that delta L vector, sort of down and to the right a little bit. We close our fingers into the page, and we see that our thumb is going to point basically radially outward. So that's going to be like the Fn acting on that particular chunk. So the force on each of these little chunks is going to be radially outward from the origin of this coordinate system that I've drawn. And you could see that everywhere around because the L will always be tangent to the circle and the B will always be into the page, and therefore perpendicular to that plane into the page and tangent to the circle is going to be radially outward. So what does that mean for the net force for this FB circle? Well, it means that it should have a net force that basically points in this direction here, FB circ, exactly in the 45-degree direction, because if you add up a bunch of forces that start out, we could sort of draw it here, there's one that points like that, there's one that points like that, and then all the rest get added, then you'll get something that points exactly at 45 degrees. So that means that we really only need to calculate one component of it, which is either the x or the y component, and then the other component will be exactly the same. That's what it means to have a 45-degree angle. So let's do that. So let's write it first. We see that how can I write this carefully? FB circ is equal to, I don't know what I should call it. Let's just call it, it's F times I hat plus F times j hat. So it has exactly the same x and y components, where fx equals fy equals f. So we need only calculate, for example, fx. So let us do that. Okay, I'm going to erase. No, I guess I won't erase. So let's calculate it. So we're looking for FB circ x, and that's going to be the sum from n is equal to 1 to capital N of FBN, the force on each, but in the x direction. So I'm really just looking for the x component of it. And let me just label this thing. This is what I mean by FBN, the force on one chunk. Okay, well, that FBN points exactly outward along this line. And I could say that that line has a theta n with respect to the x-axis. So I could write that as FBN magnitude times cosine theta n. That's going to be my x component of that thing. And these are all approximations because I've chunked it up into a finite number of pieces. Now what is FBN in magnitude? Well, we have an equation for that. It's the equation for a straight wire. So it's going to be I delta Ln B at that position. I could say B n, but it's a uniform field, so it's the same everywhere. And then times sine of the angle between delta L and B. And then we still have the cosine theta n. So what is the angle between delta L and B? Well, you might think that it's a little bit weird, but it's actually easy. We have L pointing in some weird southeast direction, but B points into the page. So it's a vector that points directly into the page. So that angle then is just 90 degrees, and sine of 90 is just 1. So that's going to be easy. Let's continue over here. So we get that it's approximately equal to the sum of I delta Ln B cosine of theta n. And you know where we're going here. We want to get to a Riemann sum. And so what is the coordinate that labels each of the chunks as you go along this object? Well, it's the theta. So theta, different values of theta give you different chunks. So we're going to want to do an integral over theta to get the whole thing. And that means we have a delta theta, we have a theta, but we need a delta theta, and that should come from this delta Ln here. So let's just look at that picture. The delta Ln is actually the delta S for this little arc length. So we can write delta Ln as R delta theta, and then we still have B cosine theta n. So we have a Riemann sum now. It looks like IRB cosine theta n delta theta. That's the approximate expression for what we're looking for. And then when you take the limit of that as the number of chunks goes to infinity, then you get the integral, IRB integral cosine theta, theta n becomes just theta, delta theta becomes d theta, and then now we need to check and see what our limits of integration are. Well, the way that I labeled this is that theta is an angle that goes from the x-axis up to the chunk. So to get the whole arc, I have to go from theta n is equal to 0 up to theta n is equal to pi over 2. So we have the integral of 0 to pi over 2. So what is that? Let's move this over. So what is that? Well, it's going to be IRB. And then we have the antiderivative of cosine theta. Well, that's sine theta from 0 to pi over 2, because the derivative of sine theta is cosine theta. And sine of pi over 2 is 1, sine of 0 is 0, so it just becomes 1, so it just becomes IRB. This whole thing goes to 1, so we just get IRB. So what do we get for the whole thing? Well, I'll just, since I'm running out of space, I'll just erase this and plug it in. As we said, it's going to be that component times I hat plus that same component times j hat. So it's going to be IRB I hat plus IRB j hat. And that's our final answer. So there we go. That's the result. Seems weird to me that it's just IRB and IL, but that's what it is. Okay, so let's move on to the last section, which is the magnetic force and torque on loops of current carrying wire. So a loop just means that we have a closed loop, and of course it's difficult to make a closed loop. I guess you could put a battery inside of a loop. So yeah, let's write down what that might mean. It could be that you have like a battery connected to a loop, and then you have a current that flows through that loop. It could mean that you have a wire that comes out of the page, so it's perpendicular to the page up until this point, and then it moves parallel to the page, to the right, and then down, and then back again, and then it goes back into the page. So you could make a loop in that way. It doesn't really matter which way it is. We're just going to assume that we have a current carrying loop. So if we take a rectangular loop, then that's going to look like this, where we have a length and a width, and we'll assume that there's a current flowing clockwise in that loop. So what is the force on that rectangular loop? Well, it's just the net force on those straight wires. So the net force is equal to FB L1 plus FB W1 plus FB L2 plus FB W2. And what do I mean by that? Well, let's say that this is L2, and this is L1, and this is W1, and this is W2. So it's a rectangle, so L1 is equal to L2. And what are those forces? Well, the magnitudes we can write down using the magnitude of the equation that we wrote down on the first page, but let's just look at the directions first. The directions are going to be given by the direction of the current, which gives us an L vector, and the magnetic field. So we're going to assume that we have a uniform field, and let's just assume the same one that we had in the previous case, which is into the page. So here's our magnetic field into the page. So what's the direction FB L1? Well, L1 is a vector that points along the top of the loop, and B is a vector that points into the page. So if you put your fingers to the right along L1, close them into the page, then your thumb points up the page. So the force on the top thing is just going to be up. What is W1? That's a vector that points down. So put your fingers down, close into the page, and your thumb points to the right. So that's going to give you a force FB W1 to the right. And of course, if you do the same thing for the bottom, you get this. And for the left-hand side, you get this. So it looks possible that all of those are going to cancel out. let's examine what the magnitudes are of those vectors. So the magnitude of FBL1 is equal to the magnitude of IL1 cross B, which is I magnitude L1 magnitude B times sine of the angle between L1 and B. So what is that? Well, L1 points in the plane of the page, B points into the page, so they're at a 90-degree angle to each other. So you get you get 1 from that because the angle is 90. So FBL1 is just equal to IL1B, but of course that just means ILB, the length of the rectangle, so that's also equal to the magnitude of FBL2. So the magnitude of the top vector and the bottom vector are equal. They point in opposite directions, so they add up to 0. And the same thing will be true for the left and the right, so they also add up to 0. So the net force on a loop is going to be 0. Now what about the torque in the same situation? So let's look at that loop again. So again we have a uniform field. Again, we'll assume that the current is just flowing clockwise. And now we want to examine the torque. So we need to choose an axis about which to determine the torque. If the torque is 0, I think I was just about to say something wrong, so I'm not going to say it. We'll think about it as we go along. So let's try and understand what the torque is about this particular axis, the z-axis. Okay, so what do we have? We have 4 forces. We already found them. So we have a force that's acting on the center of the top wire, which we could call the FL force. We have a force that's acting along the center of the bottom wire, which is also the FL. I guess this is 1 and 2, but they have the same magnitudes. And then we have a force which is acting to the right, the FW1, and a force which is acting to the left, the FW2. And I want to determine what the net torque about the z-axis is. So let me just remind you a little bit about the torque. The torque is a vector. It's equal to the position vector with respect to the axis crossed together with the force. So what's an example of that? If you have you might remember something like this. You have a bar that's holding on to a sign, something like this, and you might wonder what is the torque of the force of the sign pulling on the bar. So I guess that's a tension force. So what is the torque associated to the tension force about this axis at the end of the bar? Well, to find it, we need to write down the R associated to that force. So the position of the force relative to the axis is a vector, which I could call RT, that goes out from the axis to the point where the force is being applied. And then you see that this is a cross product, and now you've become familiar again with how to do a cross product. The direction is going to be perpendicular to both of them. So because these lie in the plane of the page, the direction of the torque must be either out of the page or into the page. And then the magnitude will be given by RF, sine of the angle between them. So let's write that down. So in this case, it would be, so if we want to find the torque due to the tension, then it's going to be, well, what is the direction? Let's give ourselves a coordinate system. So if we have x, y in the plane of the page, then if we do r cross f, fingers along r, close your fingers down the page, and you have to twist your wrist so that your hand is sort of makes a plane that's perpendicular to the page, and you find that your thumb points into the page. So that will be the negative z-axis. So the direction of this thing is minus k hat. And then the magnitude of the torque is given by RT. So that's just the magnitude of that vector there, whatever the distance out the bar is, times the magnitude of FT, times the sine of the angle between them, which in this case is 90 because of the way that I've drawn it. So that will just be 1, sine of 90 is 1. So that's a calculation of a torque, just to remind you how to do it. Now let's do it for the rectangular loop. What is the total torque? So the torque we're going to find along the z-axis. So I want to find the components of the torque along the z-axis. And it's going to be equal to the torque due to L1 plus the torque due to W1 in the z direction plus the torque due to L2 plus the torque due to W2 in the z direction. So what is that torque? Well, let's just decide whether it's positive, negative, or 0. So for L1, the torque due to L1, that is due to a force which sits at the center of the rod, which is where I've also placed the z-axis. So because I placed the z-axis there, the r vector is 0. So that's going to have 0 torque on this thing. And therefore, this thing is going to be 0. So what I've done is I've said that the magnitude of r in that case is equal to 0. I guess I can write a little note. So magnitude of r is equal to 0. What about the torque due to W1? Well, in that case, we do have an r vector. It goes outward from the axis. However, if you notice, the angle between r and f is 0. If you put their tails together, so we could do it. This is the r vector. This is the fw1 vector. The angle between them is 0, and therefore this whole thing will be 0 because sine of 0 is equal to 0. So that would be this piece of it that would become 0. For the third piece, it's going to be exactly the same as the first because the force is being applied at the axis. And for the fourth one, it's going to be exactly, well, almost exactly, oh no, exactly the same as the first. So they are, again, pointing exactly in the same directions. And so that one will also be 0. So ditto for the third one, ditto for the fourth one as the first and second. So the torque on the rectangular loop about this axis is going to be equal to 0. Now, the torque is not always going to be equal to 0. So if you have a uniform field, the force will be equal to 0 regardless of how I set it up. So I could have angled this thing a little bit, and I would still get forces that are equal and opposite because of the way that the equations are set up. You might get slightly different angles for different forces, but the magnitudes would turn out to be exactly the same, and the forces would be in opposite directions. You can try that out yourself by moving this loop around. But what if I take the loop and sort of grab hold of the right-hand side and pull it out of the page a little bit and see what the torque is in that case? Now, what has changed? Well, now the angles are not always exactly perpendicular, so now I need to look at it maybe from a different direction. So let's see. So let's say that we're going to look at the z-axis as coming out of the page. So now I'm basically looking down on this system, and I have pulled the right wire out of the page by just some angle theta. So then it's going to look sort of like my loop now in profile is going to look like this. So so we're looking again. We're now looking at L1, the top of the wire loop. L2 is behind it, and the direction of the current across the top of the loop we said was to the right there, so it's going to be moving like this. And then when it gets to this end over here, it's going to go down into the page, so we're going to get a current that goes down through, so this is I through W1. Then it's going to move back across the wire in the other direction along L2, and then it's going to come out of the page. So this is I through W2, come out of the page there. So do you understand what I've done? We started out looking in the plane of the page, the z-axis was pointing up the page, but now I've moved to sort of sit up at the top of the page and look down on the z-axis, and then I've taken this wire and pulled it out of the page a little bit, and this wire went into the page a little bit. So we end up with this perspective now. Now the field is the same, so the field we said was pointing into the page on this picture, so that's going to be a field which points in this direction. Oops. Let's do it like this. So this is our magnetic field now. It's pointing in that direction. So what happens to the torque now? Well, let's calculate it. So the torque about the z-axis is again going to be equal to L1 z plus torque L2z plus torque L3z. Sorry, I was saying this is W1z and L2z and W2z. Well, the torque due to L1 and L2 are going to be the same because there could be a force on them. So we have an I that points sort of in the southeast direction. So we could look at our force magnetic field is equal to IL vector cross B vector. So there will be a force on L1, and that will be, let's calculate its direction. It goes down and to the right, so you put your fingers down and to the right, and then you close your fingers up the page, and there will be a force that points up on the center of the wire. So we would draw that as something like this. Oops. We would draw that as something like this. So this is FBL1. It points out of the page. And that, I guess, is exactly the same as what we saw here. So even though we've rotated it slightly, we're still getting that force that's up. However, that force is going to be applied at the center of the object, and therefore that's right on the z-axis. So the r vector to the force is again going to be 0. So that's going to be 0 there. The same thing will be true about L2 there. So the only question is what happens with W1 and W2. Well, the current going through W1 is now going to be pointing into the page in this perspective. So that's the direction of our W1 vector. So we could draw like a W1 vector like this. And if we take the right-hand rule for that, so point your fingers of your right hand into the page there, and then you want to close them in the direction of the magnetic field, which goes up the page, and you should find, well, into the page and up the page form a vertical plane that intersects the screen, and perpendicular to that, you should find that your thumb points to the right. So the force on this particular section of wire, I'm going to get these things out of the way, is going to point directly to the right. So this is FW1, like that. Now if we look at the other side, over here, then we have the current coming up out of the page. So point the fingers of your right hand out of the page and then close them up the page. So you're sort of folding your finger up the page, and you should find that your thumb points to the left. So this is going to be FW2, pointing like that. Okay, so what does that tell us? Well, the R vector for each of these points along the L wire because it goes from the z-axis to the point at which the force is applied, and that is like this. So this is the RW1 vector, points like that. And as you see, the R vector and the force vector are no longer parallel. There's an angle between them. So we have an R vector that looks like this, and we have a force vector that looks like this. And there's an angle between them. So this is the angle RF right there. So if there's some angle here, theta, then that's exactly equal to theta. So we get a torque, which is going to be RW1. So we have 0 for the third one, and then we'll get something for the fourth one. So it's going to be RW1 times the force, which is FW1, times sine of the angle, theta RF, so that's going to be sine of theta. And then we have to decide whether it's going to be positive or negative along the z-axis. So remember, torque is equal to R cross F. So you have to put your fingers along the RW vector and close them towards the F vector. And where does your thumb point? Well, it points out of the page, so that is along the z-axis. So that's going to be plus, this plus sign is still a plus sign because the z component is positive. Okay, so we get something there. Last time, remember, we got 0 there. Now the only question is whether we're going to cancel it out over here. So let's examine that. So now we look at the R vector to this force. So this is RW2. And the magnitude is again going to be RW2, FW2, sine of the angle theta, because you can see that they're still going to have exactly the same angle between them. Let's draw it. So we have RW2, we have FW2, and they have an angle theta between them. Now, what's going to be the direction of the torque using this equation? So we point our fingers along the R vector, we close them toward the F vector, and you see that your thumb points out of the page again. So this again is a positive torque in the z direction, meaning it points along this z-axis that's coming out of the page. So these two things do not cancel out, they actually add together. And they will have the same values because RW1, what is that? That's L over 2. And the force W1, that is going to be I W B. And then we have the sine of the angle between W and B. Well, W is a vector that points into the page, and B is a vector that points along the page, so that angle is 90. So we're going to have a sine of 90 there. And then for the second wire, we have exactly the same thing. IWB sine of 90. So we get LIWB like that. And that's going to be the torque. So we find a torque in the z direction when you angle the wire loop with respect to the magnetic field. So what does that actually mean if you have a torque in the z direction? Well, remember that you can think about the torque as causing an angular acceleration in the same direction. And so the angular acceleration that you'll get from this torque, if you have a positive z torque, then that means a counterclockwise torque. So you're going to get an angular acceleration in this direction. So the torque of the magnetic field on the loop tries to bring the loop back to being perpendicular with the field. Remember, we saw that when the wire loop was aligned here, as we did on the previous page, there was no torque. But if you angle it off here, then it will try to bring it back in alignment with the field. So a magnetic field takes a wire loop and tries to align it with itself. And that's basically the same thing that's happening with compass needles being aligned with a magnetic field line. So we have a shorthand way of describing that, and let me just write it down for you. So we see here that we could write this as I times W times L times B, or I times the area of the loop times B. And we did that for a very simple geometry. We did it for a geometry of a rectangle, but it turns out that it's a general result. We could have made a much more complicated loop and we would get the same result. So the way that this is normally expressed is in terms of something called a dipole moment of the current loop, and we write the dipole moment as mu is equal to I times A, and that's the magnitude of it, but we could think of it as a vector in terms of the A vector, where the area vector has a normal vector that points perpendicular to its surface. So on this picture, the normal vector would be pointing, like this, perpendicular to the surface of the loop. And we can express the torque then. So the torque on a loop, generally, is going to be equal to, well, we found that it was IA times B. Oh, I think I left out something here. What did I leave out? Oh, I lost these sine thetas here. That's why. So there should be a sine. So this was just the force, and there should still be a sine theta here. And so there's a sine theta in the result here, and there's a sine theta in the end result here. So this sine theta makes you think that there was a cross product going into it, so that the torque on a loop can be represented as a vector, which is the magnetic dipole moment crossed together with the magnetic field. So you have, let's try and draw some sort of generic picture of it. If you have a magnetic field that looks like this, and you have a loop that maybe makes an angle with respect to that field, so something like this, then you can say, well, there's an area vector that points outward like that, and that's also the direction of the magnetic moment vector, because the magnetic moment vector points in the direction of the area vector. And if there's an angle between the magnetic moment vector and the B vector, then you will get a torque. And that torque will be such that it rotates this thing back so that the magnetic moment points along the B vector. And we saw that in the case of the rectangular loop, but it's true for generic loops as well. So we'll end there, and next time we'll talk about how magnetic field is generated by moving charge.